In the third part of the lecture, I will discuss the phenomenon of waves. I will define the basic characteristics of a wave and the basic parameters that are used to describe waves. I will also talk about the interaction between waves, and I will finish with the concept of standing waves. Waves are disturbances in a medium created by oscillations of the particles of the medium. A simple example for waves in a medium would be waves created in a rope or a string. So if you're holding a rope by one end and you tie the other end and you shake the rope up and down, you're going to create waves in the rope and they will be visibly moving away from you. However, you will also notice that the rope itself does not move away from you, which means that the particles in the rope are actually not moving away, they are simply moving vertically up and down. Let's illustrate that concept. So here is the rope. It is tied at one end, the other end is free, and so at the free end I'm going to have a source of disturbance, or in other words, a device that generates force at that end of the rope, and so the force will be generated in vertical direction, up or down. That's going to cause the particles of the rope to vertically move up and down like so. Let's sketch that as well. Let's look at several particles in the rope. And how they move. So let's first start with that first particle here. Since the direction of the applied force is up, so this particle will be moving up. The particle next to it will also be moving up, but a little bit less. And so will be the next one until the particle at the very top right here is actually stationary at this particular moment of time. The particle next to it now is moving down, and so is the other one, and that, and that, and that. And the particle that is passing through the equilibrium position of the rope is also moving down. And so then these particles here are moving down as well, but a little bit less, until we reach the lowest point. This particle is stationary. After that, the particles are starting to move up again until the top particle right here, which is not moving. And then after that, this particle is moving down. And so each individual particle essentially is moving along a vertical line, up and down. You can think of those as tiny masses attached to individual springs that together oscillate in that manner. And so the particles of the rope simply oscillate up and down, but as a result of that, the disturbance that's generated in the rope is propagating away from the source of disturbance. So here, the direction of propagation is to the right. So for waves for which the oscillation of the particles of the medium is perpendicular to the direction of propagation, we call those waves transverse waves. So transverse waves are waves with direction of propagation perpendicular to the direction of oscillations of the particles in the medium. We have a second type of waves, or second kind of waves, based on the direction of propagation and the direction in which the particles of the medium oscillate. Those are longitudinal waves, which are waves for which the particles of the medium oscillate parallel to the direction of propagation. And an example of a longitudinal wave, and that is the only existing longitudinal wave, is the sound wave or sound waves. Let's quickly sketch what happens in air when sound is generated. So consider a loudspeaker. Loudspeaker has a membrane here, which, when the electrical signals come into the speaker, causes the membrane to oscillate back and forth. Well, this membrane will physically interact with the molecules or air molecules around it, and that's going to create compressions and rarefactions regions of the molecules in the air around the loudspeaker. So the molecules close to the loudspeaker will get closer to each other due to the physical interaction with the membrane of the loudspeaker. That's going to create a region of higher density of molecules or higher pressure. And this is called a compression. So this compression will move away from the loudspeaker, and it's going to be replaced by a volume of air that has less density or less molecules per unit volume. So that is a rarefaction. After that, another compression is created. It moves away, followed by rarefaction. Compression, rarefaction, compression, rarefaction. And this is the periodic nature of sound waves. So here I have one compression, two compressions, and in between is the region with less molecules. That is the rarefaction. And so, as you can see, molecules of air moving away, but of course, they collide between themselves and with other molecules around them, so eventually they will start to return back to the loudspeaker, interact with the loudspeaker, a new compression is created, followed by a rarefaction, moving away, and then more molecules are coming back, another compression is created, followed by a rarefaction, and so on and so forth. So, the molecules of the air, which are the particles of the medium that carry the sound wave, actually oscillate back and forth like so horizontally, and the sound wave propagates horizontally as well. And so that is what the longitudinal wave is. The direction of propagation is parallel to the direction of oscillation of the particles of the medium. Now let's talk about superposition of waves. Superposition of waves is an effect that occurs when more than one wave occupy the same space at the same time, in the same medium. When those waves meet, they interact to produce a combined wave, but they do not stop their propagation in the medium, nor do they affect changes in each other or on each other while interacting. So the process of combining two waves into one wave is called superposition. Let's look at what's happening when two waves interact with each other in the same medium. I'm going to use, for an example, two individual pulses generated on the same rope. So here is my rope, and so I've created two disturbances, wave 1, which moves to the right, and wave 2, which moves to the left. So I applied force on each end just once to create that pulse. So wave 1 has amplitude A1, wave 2 has amplitude A2. And so these two are traveling towards each other, and at some point they will start to overlap. So when they start to overlap, at some point the resultant wave that we will see on the rope will look like so. So we still can differentiate the peaks of each of the pulses, but now they're starting to merge with each other. Well, what happens when they are exactly positioned at the same position? When the two completely overlap, we are going to get a resultant wave that will have an amplitude that is equal to the sum of the amplitudes of the two individual waves. And then after the two waves have interacted, they will continue moving on their own, in their own original directions. They will, as if they never had met each other. So they affect each other in no way, as they superimpose right here on the rope. Let's also look at the interaction of two waves with the same amplitudes. One that is generated above like so, and the other one is on the other side of the rope below, and they're moving towards each other. When the two start to interact with each other, we can still again make out the individual peaks, but they start to combine around this region. So what's going to happen when the two waves overlap completely? When the two waves overlap completely, since they have the same amplitudes, at the point of overlap, these two amplitudes will cancel each other, and at that moment of time, there will be no wave on the rope. And then the two waves will pass each other and continue their own way, having the exact same parameters as before the interaction. So they have never, as if they have never met each other. So we have two general possibilities. The two waves interact with each other when they are positioned like so to produce a combined wave with an amplitude which is equal to the sum of the two amplitudes. Or we can have the waves in opposite orientations, and when they meet each other, the amplitudes will cancel depending on what they are. In this case, since the amplitudes are the same, they completely cancel each other. So the resultant wave at the moment of interaction is zero, with zero amplitude. Now I want to introduce the concept of periodic waves. When a source of disturbances in a medium produces waves with steady frequency and amplitude, we say that the generated waves are periodic waves. Periodic waves are characterized with the following parameters: amplitude A, frequency F, period T, wavelength lambda, and speed of propagation V. Let's explain what these parameters mean in terms of periodic waves. So I have a rope, and a periodic wave is generated on the rope. The amplitude of the wave is defined as the maximum displacement of the particles of the medium from the equilibrium position. So the equilibrium position of the rope will be here, and the maximum displacement distance is that, or that, or that, or that. So that is the amplitude. So the distance from equilibrium to the maximum displacement on either side is the amplitude. The definition of frequency of the wave is exactly the same as for simple oscillations. So the frequency is the number of cycles per unit time. So here the question is, what is a cycle? The definition again is pretty much the same. A cycle is a portion of the motion of the wave which is unique, and after this portion is passed, the next portion looks exactly the same or identical. And so here, if we start at this point and move along the wave and we get to here, all of these points or the wave here, it's all unique. There is no repeating pattern. But once we get to this point and start going again along the wave, we see that the pattern now repeats. It's exactly the same as this pattern. So then one cycle will be just that much of the wave. After that, we have another cycle. And so the frequency is the number of cycles per unit time. or more accurately per second. So how many of those cycles will pass through a certain point of the rope in 1 second? That is the frequency. The period is defined as the time for one cycle of the wave to be completed. And so one cycle of the wave is defined by the positions of 2 points along the waveform beyond which the pattern repeats itself. So again, here we have the pattern as unique as it is right here, and then after that it starts to repeat itself. So the time for the wave to pass between these 2 points is the period of the wave. So let's label that period T. So I can also measure the period of oscillation between some other points. For example, I can choose the 2 peaks here. So the time that it takes for the wave to propagate between those 2 points, between those 2 peaks, is also the period of the wave. And then, of course, I can choose the time between that point of the wave and that point of the wave. That is also the period. So as long as you follow the requirement that you have a unique portion of the wave before it starts to repeat itself, you can always calculate or measure the period of that wave. The wavelength of a periodic wave is defined as the distance between 2 points on the waveform beyond which the shape of the waveform repeats itself. So the wavelength can be found by considering any 2 such points. So what does that mean? Well, again, here are 2 points of the waveform beyond which the shape of the wave starts to repeat itself. So the distance between those 2 points is the wavelength of the wave. So let's label this with lambda. So this distance is the wavelength lambda. So as you can see from the definitions of a period and wavelength, essentially the time for one full wavelength of the wave to pass through a certain point of the rope is the period of the wave. Similarly to the period, I can measure the wavelength between any 2 points as long as the pattern is unique between those 2 points on the waveform. So for example, I can choose to measure the wavelength between this valley and this valley. So that is also the wavelength of the wave. And finally, the wave speed is the speed of propagation of a wave, and it is related to its wavelength and frequency or period. So the speed is the product of the wavelength and the frequency, and we know that frequency is equal to 1 divided by the period, so the wave speed is also equal to the wavelength divided by the period. So what are the units for those parameters? For amplitude, we have the basic unit is meters, but of course it can be centimeters, it can be millimeters, any unit of length, but the base unit is meters. For frequency, we already know it's the hertz. For period, again, the units can be anything. The base unit would be the seconds. Otherwise, we can have minutes, we can have hours, and so on and so forth. The units for wavelength. This is the length of the waveform between 2 points on the rope. So this will be measured in base units meters, but it can be also centimeters or millimeters or any other denomination of a length unit. For speed of propagation, we have meters per second. Now let's do one example applying the definition of wave speed. Find the speed of a wave on a guitar string if the wavelength is 20 centimeters and the frequency is 400 hertz. So we want to find the the wave speed V, which is calculated as the product of the wavelength and the frequency. Since I know that the units here must be meters per second, that tells me that the wavelength units must be converted. So this is 20 centimeters times 400 hertz, which is equal to 0.2 meters times 400 hertz, which gives me 80 meters per second for the wave speed of that wave. In the discussion so far, I talked about a wave that's propagating on the rope, and one end of the rope is fixed. Okay, but what happens to the wave when it reaches that fixed end? It's very simple. The wave will just reflect, and then it starts to propagate in the opposite direction. And so now we have two waves that propagate on the rope, but they propagate in opposite direction. And so we now can apply the principle of superposition to obtain a picture of the wave that will be settled on the rope when the two waves interact with each other. So here is the generated wave. It travels to the right. It reflects from this end. What does it look like after reflection? Here is the reflected wave in red. So the wave starts to move like so, to the left. Let's also indicate the directions on the waves themselves. And so the two waves move in opposite directions. They interact with each other on the rope, and then we see this steady picture that does not change with time. So we have areas where the two waves completely cancel each other out, and then we have areas where the two waves enhance each other to produce double the amplitude. And this picture is stationary with time, meaning these areas here do not move around, they just stay here, 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 here. And so that type of wave is called a standing wave. So the two waves will meet each other along the rope and will superimpose with each other. As a result, a pattern that does not change with time, called standing wave, is created on the rope. And this is what an example of a standing wave is. Now we can have standing waves with more loops. We can have standing waves with less loops. But this is what a standing wave looks like. Let's consider a string or rope that is fixed at both ends, and then a standing wave pattern is created on this rope. The points where there is no amplitude are known as nodes of the standing wave. So in this particular example, we have 1, 2, 3, 4, 5 nodes. And the areas at maximum amplitude are known as antinodes. And so we have 1, 2, 3, 4 antinodes. So for a standing wave, when the two ends are fixed, we always have one extra node for the number of antinodes available. So here we have 4 antinodes and we have 5 nodes. When the number of loops increases, so that means more antinodes, that means more nodes. If the number of antinodes decreases, that means also less nodes. And so one more time, nodes are points with zero amplitude of oscillations, and antinodes are points of largest amplitude of oscillations.